Hi. So welcome back to the lecture series on algebraic geometry. We have started with the discussion with varieties, and in last lecture we have defined what is something called algebraic algebraic sets, and also we have defined how to construct a topology via these algebraic sets, and just considering this algebraic set to be the closed set is enough to define the topology, and that is known as Zariski topology. So in fact we have also introduced something called, it is just like a revision kind of thing, irreducible topological space, and also there are some properties that we have seen in case of what irreducible topological space should give us. So here are the properties, like if we have any topological space X, then of course if you take any two open sets, non-empty open sets, the intersection always should be non-empty. Okay, so it is a if and only if condition that if we have any u1 and v1, these two open sets, then the intersection will be always non-empty, whereas both are a proper open subset. It is none of these is a phi. Okay, and in fact we have also seen that if we have any open set of a irreducible topological space, then it is also the closure that open set is always irreducible, as well as its closure is entire X, means the open set is dense. Okay, so now there is also one observation that one can expect, that is, suppose X is a irreducible topological space, okay, and let us consider that Y is let us consider Y. Let us consider a general setup. Let's take S is a topological space itself. X is a topological space, and Y is a not closed, just take Y irreducible subset of X, then Y closure is irreducible. Means suppose we have a topological suppose X is a topological space X, and let us consider this my X. If we have any, let's say Y, then let us take any other, the smallest open closed subset that contains this. So this particular closed subset will be always irreducible. For example, suppose let us take, if Y closure is not irreducible, that means we can write to be as Y closure equal to let's say C1 intersection Y closure union with C2 intersection Y closure, where C1 and C2 both are closed in X. Okay, so that means I should write I can let's say, so what is my Y? So the most natural choice for Y can be that C1 intersection Y union with C2 intersection Y. Okay, and how to prove that both are proper open subset? For example, suppose C1 intersection Y, if this is phi, means C1 intersection. Okay, so that means C1 doesn't contain any element, it doesn't contain any one element from small y. So for example, suppose small y closure, small y, but this particular one this is non-empty. Okay, so as it is non-empty, so C1 intersection with y interunion derived set of y. So C1 intersection with y union with C1 intersection d of y. Okay, so that means this is phi. So what about this one? So I should get it here only C1 intersection dy. So if we take any okay, so okay, anyway, so I mean this is there only C1 d of y, but you see that if we take any small I belongs to y closure, so I mean let's say small I belongs to y, let's say small I belongs to y, if we take any element small belongs to y, so of course this should not belongs to here only, right? So this must belongs to here. So always see y should be subset of C2. So y subset of C2 means y it is a smallest closed subset contains C2. So y closed subset of C2. This should be always. So that means this also should be non-proper. Okay. So this is how one can define the things. Alright, so if we have this closure of irreducible subset is if you have any irreducible subset y, and then you should find that the closure of the irreducible subset is always irreducible, right? The closure of irreducible subset is always irreducible. That's what I was saying. Okay, so this is a very beautiful observation. In fact, this can be helpful to get, I mean, while we study the dimension of variety, then it will be helpful for us to use this fact. Alright, now let us go ahead. So now we have seen that suppose we have K is a algebraically closed field, because this is the main basic stuff that we are going for considering throughout the entire discussion. So okay, and let us consider a power nk. So it is affine set, is an affine space of dimension n. Okay, so it is ank. So it is a topological space. So as it is a topological space, then we can talk about closed subsets of a power nk. Okay, so as you can talk about the closed subset of all these a power nk, then what we can do, that means we can always also talk about more special, that is irreducible closed subsets of a power nk. So these kind of subsets are called affine variety. Okay, or affine algebraic variety. So that means it is also basically it is irreducible, means irreducible with respect to the subspace topology. Okay, and if we have any affine variety, then the subset of any open subset of affine variety this is known as quasi-affine variety. Okay, so these are the first objects to study in algebraic geometry. So okay, but before going in detail study with this, let us see a very interesting thing, that suppose, so we have ANK, right? This is affine space. Of dimension n. Okay, now let us consider Y is subset of ANK. Okay, so I mean, how does this ANKs look like? It's nothing but K1 come up to Kn such that small k belongs to the field K. Okay, now I define I of Y to be as set of all small f of x1 up to xn belongs to k of x1 up to xn such that f of k1 up to kn is 0 for all k1 up to kn belongs to nk. That means it is basically the set of all those polynomials that get vanished at in the entire ANK. Okay, so basically the thing is that I'm sorry, this belongs to Y, this entire Y. So basically, so if we take any, let's say, small f from here, then that means basically f of x1 up to xn, this belongs to k of x1 up to xn such that Y is subset of z of f. Okay, this is how one can define this idea, define this set. So first of all, is this set empty? Of course no, because always the zero polynomial must belongs to I of Y. So is it a subgroup? Is it a subgroup? Let us consider f of x1 up to xn and g of x1 up to xn from I of Y. Then we consider f of x1 up to xn minus g of x1 up to xn. Okay, we consider this. So this is basically, if we apply any small k1 up to kn, if we take any element from this capital Y, I should always get f of k1 up to kn minus g of k1 up to kn. This is 0. Okay, so this is 0 means this is 0, so this entire mine is always 0. So that means if this is empty, so as it is empty, that means what? That means that means f minus g, this belongs to I of Y. Okay, so that means this is basically a subgroup. So now as it is subgroup, so can we define what is the next one that one can think of? So as it is basically subset of k of x1 up to xn, the most natural choice that one can think of, is it an ideal or not. So it is also very easy to check that suppose if we take any element, let's say gamma of x1 up to xn belongs to k of x1 up to xn such that gamma of x1 xn into f of x1 up to xn, this is nothing but if we apply this one and apply k1 up to kn here, I will get as 0. So that means gamma times f is must belongs to k of x1 up to xn. So as it is there, hence I of y, this is an ideal of k of x1 up to xn. So this is how one can think of. So it is an ideal. So as it is an ideal, so that means if we have any subset of a n k, I can generate an ideal I of y and can do this entire operation over there. Now what about the reverse picture? So what is the reverse picture? So let us consider the reverse picture is always something like that. So let us consider suppose not small, let us consider small s is subset of k of x1 up to xn. Then we consider z of s to be a set of all a1 up to an belongs to k power n such that f of a1 up to an is 0 for all a1 up to an belongs to s. Oh, sorry, I'm sorry. Such that for all f belongs to k of x1 up to xn. So this is how we define z of s. So it is basically the 0 set of the set S. So but that means we basically have got two-way transport like this. Suppose we have here that is subsets of k of x1 up to xn. In fact, it is always better to choose an ideals. And here I have let's say subsets of A and K. So one way is very crucial, like this is via Z, and another way is like this, here to here, this is via I. So that is like this. Okay, now we have got two-way transport. So what about that? Suppose we go from here to here via this path and then again come back here. Should I get the same thing here again or not? So let's verify. So suppose you have chosen an ideal, let's say I have chosen, let's say not this, let's consider I be an ideal. So what about Z of I? So Z of I means Z of all those elements or all those elements in A and K that vanishes every polynomial in I. Okay. Now if I again apply capital I on this, what it should be? So the most natural choice it should be that it should be radical. So you see that just one thing that okay, so you see if we take any element from here, let us take small I. This belongs to this ideal capital I. Okay, not small I, let's say small I of x1 up to xn is I chosen from A. Okay, so that means what? That means I of wait a bit. For example, let us consider that small r, let's take small r belongs to I of zi. So then what I should get? That means for all if for all not okay not let's take I of x. This belongs to here. That means for all k1 up to kn belongs to z of I of x1 up to xn, it is get vanished at k1 up to kn. So that means this particular polynomial get vanished at entire z of I. So z of I is what? Z of I is basically a closed subset, right? Z of I is basically a closed subset. So if it is getting vanished entire z of I, so that means by Hilbert-Nullstein's theorem, by Hilbert Nullstein's theorem, I of x1 up to xn, this belongs to radical of alpha. Radical of I. So conversely, so that means this one is subset of radical of I. Conversely, if we take any element, let's say j of x1 up to xn is belongs to radical of I, means the power of this set, okay, this must get so that means this is gets vanished at entire z of I. But this is how we have defined z of I, right? So that means j of x1 to xn full power n, this belongs to I of zi. Okay. Now this belongs to there. Okay, I mean, now one thing that if we just apply any element, let's take any element a1 up to an. So if we just take here now as k of x1 up to xn is an integral domain, so j of this particular power of this polynomial get vanished at a1 up to an means what? As k of x1 up to xn, this ring of polynomials over k is a integral domain, so that means j has a root at a1 up to a. So that means j must belongs to here only. So that means this one is basically same as radical of I. Sorry, it's not a visual color to okay, fine, let us this one remember. Okay, on the other hand, so if we just, that means first you consider here one ideal, go to here z and suppose it is I, here you will get z of I, and again via this we will get it here. So initially it was I, then you get z of I, again you get radical of I. Means our larger ideal than I. Okay. Now what about the conversion? Let us consider that suppose we have an open subset, let's say y is here, then what if we applies I and then in z, let's say, so y subset of nk then what about z of y? So that means what about z of y? So z of y means set of all those let's see small, so yeah, sorry, not z of y, so I of y, sorry, I of y, set of all small f of x1 to xn belongs to k of x1 up to xn such that f of a1 up to an is 0 for all a1 up to an belongs to y. Means all those polynomials that get vanished at if entire y. So now if we apply z of y on this, that means this should be a closed set, right? So what should be the closed set? The most natural choice of the closed set that one can cook up with y is nothing but the y closure. So this is the thing, and let's verify whether it is correct or not. So for example, suppose so I mean you see that y is always subset of z of I by, right? That is by definition. So as it is there, and this is a closed set, so y closure, this must be inside beta phi by. So one side is always, so it is very obvious. What about the other side? So other side is, so suppose W is a closed subset and Y is inside W. Okay, So of course, as it is a closed substring, we can consider W equal to Z of alpha and Z of beta. Okay? Z of beta, where beta is ideal of. Okay, so that means Y is inside W, means Y is inside Z of beta. So now if we take I, apply I at the both sides, so I of Z of beta means what? All those prime ideals that get vanished, all those polynomials that get vanished in entire Z beta. So that means this must be contained in I of Y, because whatever polynomials will be here, that must get vanished by everything in Y, because Y is inside Z of beta. Because I mean, this is the larger set, I mean this is a smaller set, this is contained here. So once we are targeting this, means it will be always satisfied over Y. That means this property is always there. So in fact, this is I of Z of beta is this, but what about beta? So of course beta will be here, right? So I of Y, this is an ideal that contains beta. Okay, so that means we have that so beta, so Z of I of Y, this should be contained in Z of beta. So that means Z of I of Y, this should be contained in Z of beta means W. Okay, so Z of I is contained in W. So that means it is the smallest closed subset that contains Y. So that should be anyway Y closure. So this is another thing that one should keep in mind. Okay. Okay. So you see that anyway, as maybe we have both sided way, but it is not anyway preserving the entities, right? Means if you take any radical from here, once you traverse the entire path, you are getting something bigger than that. Again from here, if you take any any subset from here, you traverse the entire path and get here. So that means if you want to get back anything, so what are the criteria? I mean, if you want to preserve these entities, what are the should be restrictions over the ideals as well as subsets? So that means so it is, if you want to preserve the direct, so if you want to preserve the entities from via this, then radical of I, this should be the same as I. Okay, that means this I should be a radical ideal, because then only it will be same as I. Okay, because this is the in general setup that we have constructed here. So just add an extra condition on this, that is the radical ideal and what about here? What about here? this should be closed. Y should be closed. So closed means this is a algebraic set. This is not really algebraic sets. So that means you can add here. That is algebraic sets. Okay. So that means if we just want to make another comment that from radical ideals of k of x1 up to xn I have one direction here, that is up to the algebraic sets of nk and k to k, that is via z, via I. So this kind of both way direction where the entities are getting fixed or preserved, this kind of correspondence is basically said to be as one-to-one inclusion reversing correspondence. So this is a word that this terminology that as I have just only found in Robin Harshon. I don't know whether he has just tried to make a more generalized version of bijection, because anyway there is, we cannot say that okay, this is a either it is a, in fact a set mapping, but we cannot say that okay whether it is continuous map between topological spaces or homomorphisms on anything. I can't say anything like that, because the suitable structure is not associated with these two things as well. So that's why he has just used more generalized notation, that is one-to-one inclusion reversing correspondence. Like inclusion is getting, if you reverse these inclusions, then also it get same. The result will be not changed. All right. So you see that once I have talked about algebraic sets, now what if I consider this something called irreducible? Let's take irreducible subset. One irreducible closed subset. What if? So that means if I apply IY here, you can apply IY here. Okay. So what will be IY? What can be the property of IY? We will just argue with that this should be prime. So how to get is a prime ideal? For example, we just consider let's take any f times t, this belongs to I of y. Okay, so then let us consider we have zf, right? So let us consider zf. This is a closed subset, intersection with y, and zf, zg with y, and interunion. So these should be same as y. Alright? Because if you take any, let's say small y, from small y, let us take any element from small y, so it is basically tuple, right? So as it is small y, so either this will get if fg times that particular element will be 0. So fg of that element is, so either f of that element is 0 or g of that element is 0, because the ring is the integral domain itself. So that means either it is in z of fy or zg of y. That means y is basically something like the same with this. Now if f and g both are not in iy, that means this is not phi, not itself y, this is not phi, not itself y. So that means both are proper subsets. So that's why you can get that y is not irreducible. Here's the contradiction. Okay. So this is how one can draw the contradiction, that means I of I should be prime ideal. Again, what about the reverse statement? Let us take any prime ideal from here. So what about ZP? So ZP is nothing but, we will show that it is irreducible closed subset of A and K. Okay. So what about ZP? Let's see. So let us consider that ZP can be written as y1 union y2. So what about I of ZP? It is I of y1 union with I of y2. So I of ZP means rad of P, and rad of P is nothing but P, because radical of prime ideal is always P, same as I of y2. So it is, as it is prime ideal, so it is basically, oh, I'm sorry, so it should be intersection. So it is intersection of any two ideals. So by prime abundance lemma, you can say that either P is same as Iy1 or P is same as Iy2. So that means this inclusion reversing principle basically gives a equivalence relation between the irreducible closed subset and radical ideals, and more precisely the irreducible closed subsets and the prime ideals. Okay, so let me just have a note that suppose we have irreducible closed subset y, then it is irreducible if and only if I of y this is prime. Okay, so your exercise is to that verify all the prime ideals of Kx using the above condition. This is a small exercise. It's very, very trivial. Just you try by yourself. Okay. So in the next class onwards, we will continue with our more discussion with this. So just go through the previous notes, understand, try to grab these short discussion, and we will continue with the next lecture onwards. Okay, thank you very much.